So we've got to try and solve this problem. So we've worked out that W is given by these three things. Okay, so if we're going to do the even first. So W is going to be, so for the even solution, it's going to be A1 e to the kx. And since it's even, this has to also be A1 e to the minus kx. So this is x is less than zeta and x is greater than zeta. And then in between, since it's even, we're only going to have cos kappa x. X is between minus zeta and zeta. Okay, so all we've got to do now is we've just got to match the function and its derivatives at plus or minus zeta. So, and since it's even, if we match it with plus minus zeta, we'll get the matching at plus zeta. Okay, so let's assume here, it doesn't really make any difference which one we do from the symmetry, but let's say at x equals zeta, we have W and the x derivative match. So what we get is, we get cos of kappa zeta. Remember that kappa is a function of k. Really important to have that in mind. It's the square root of b minus k squared. Okay, cos of kappa zeta. Whoops, I've need my constant here, obviously, b1. So the solution, homogeneous solution is going to always work. We're going to have A equals 1 equals B1 equals 0. We're looking for non-trivial solutions. So we're looking for some determinant cis to vanish. This is A1 e to the minus k zeta. And then the derivative is kappa B1 sine kappa zeta with a minus. This must equal the derivative here, which is minus k A1 e to the minus k zeta. Now if we write that as a matrix system, we get some matrix here, and our matrix is going to be e to the minus kappa zeta cos kappa zeta and k e to the minus k zeta minus kappa sine kappa zeta. Okay, so everything hangs on this matrix here. So we need the determinant of this matrix to be equal to 0 for this to have a solution. So let me clear that and write that condition down. Okay, so we've got it. We just from matching, we get this matrix condition. We've obviously got the solution A1 equals B1 equals 0. If this matrix is invertible, that is the only solution. So we're looking for whether the determinant of that is 0. Not totally trivial to solve that, but we've got the determinant of this matrix e to the minus kappa zeta minus cos kappa zeta determinant must equal 0. So we multiply across here and we get minus k e to the minus kappa zeta sine kappa zeta plus k e to the minus kappa zeta cos, oops, and there's got to be a kappa, not a k here. And so then, be careful here. Be very careful. So basically, I'm getting my k's and kappas muddled up, called all kinds of problems. That's a kappa, and that is a kappa as well, right? Kappa, kappa, and that's the derivative here. That's a k. Cos kappa zeta equals 0. All right, great work. So we can cancel out the exponentials. They're never going to be 0. And we can write this equation down as tan of kappa zeta, dividing by cos here, is equal to, and it's going to be k over kappa. So that's how it's called a transcendental equation. God knows if I spelled that correctly. Pretty sure I haven't. It's transcendental. I don't know how the hell to spell it. The spelling is terrible. It's a transcendental equation. All right. So we've got to try and solve this equation, and we've got to think about what this actually is. And it's easiest to think about it in terms of kappa now rather than k. So we've got to just look at the solution of that equation. And they commonly arise in these eigenvalue problems that you get these transcendental equations. Unless the system is super trivial, like the examples in the heat equation and things. All right, so what have we got here? We've got kappa is the square root of b minus k squared. So we can rearrange that, and we get kappa squared is b minus k squared. So we get k squared is equal to kappa squared k squared is b minus kappa squared. So we get k is the square root of b minus kappa squared. All right, so here's our equation, and what we need to, so the k can only go between, we've got to have k positive, kappa positive, so k can go at most the square root of beta. Okay, otherwise there's no solution. We can try outside of that range, and you can, solve the equation and see, but you're only going to get solutions here if k is between 0 and the square root of b. All right. Outside of that thing, there is no solutions. There's only a finite number, and they lie between this in this interval. So let's try and have a look at the picture of this solution. Okay, it's not drawn in the notes, but it's quite handy to see it. So here's tan. So tan looks like that. All right. Great job of drawing tan. There's the picture of tan. And this is pi over 2, 3 pi over 2. Okay, and this is pi. Okay, so that's tan of kappa times, okay, I've got to be slightly careful here. Tan of kappa zeta. All right, it's probably easiest to just assume here zeta is equal to 1 for example, for the picture I'm going to draw. Okay, we'll just assume that. Just to make our life simple. Okay, and then we've got to draw a picture of the other curve here, which is colour wheel. The curve is k, which is the square root of, this is on this axis is kappa, the square root of b minus kappa squared over kappa. Okay, so let's have a look at this. So b is sort of the height of it. So somewhere down here is some point where kappa is equal to the square root of b. Right? And that's when this thing vanishes. And we can't continue it on after here. The curve doesn't go anywhere, and the tan would become hyperbolic tans. This becomes imaginary, and there is no solution. And it's And we know it comes down from infinity up here. So the curve comes down sort of like that. I'm trying to draw it as best I can. And it hits here. Right? And we're going to have 1, 2, 3 solutions. Okay? And we know that the square root of b here is greater than, this thing here is 2 pi. So the square root of b has to be greater than 2 pi. And if I lower the square root of b, I'm going to get a solution curve that's going to come down sort of like that. It's only going to have 2 solutions. Okay, I'm only going to get a finite number, but then I'm going to get 2. But I'm always going to have 1, no matter what. Okay, there's always 1, at least 1. So you're going to get a finite number of solutions spanning out depending on the ratio of b to zeta, where kappa, where these curves intersect. Okay, the only way to find them, this picture shows you they exist and it shows you the interval they exist on. The only way to actually find them is numerically.